This is Team 6's interim presentation on our product analysis. Our team is focusing on a consumer-grade electric heat gun, which generates heat through induction and transfers the heat through convection by a small fan. The flow of heat is directed through a short pipe, allowing for a precise, directed heating to a desired area. Here you can see the fully assembled and exploded view of the components that make up a heat gun. At this point, we aren't sure what the internal electronic subassemblies look like. The shape for them are consequently mock-ups, which we intend to refine later in our redesign. A side note for this presentation is that the term assays and subassemblies are used interchangeably throughout. We have also found technical documents that show an exploded view of a similar heat gun model in better detail, and we are using this information to help us with our analysis.
According to our market research, the global annual demand for heat guns is roughly 7.78 million units with a CAGR of 4.5%. The US market for heat guns comprises approximately 30% of the global market share, or 2.3 million units annually. We estimate that our annual production volume to be roughly 50,000 units, which is about 2% of the US market share. The primary customers that we have identified are electrical contractors and home-owning DIYers. The secondary customer group would be HVAC professionals and plumbers.
In the functional analysis, we identified the main task function to be heat materials, and this includes the basic functions, primary basic functions, supporting functions, and the primary supporting functions. Then in the assembly sequence analysis, we created two fishbone diagrams. In these two diagrams, the assembly is essentially composed of many smaller subassemblies attached to one major component, and the order of the assays are attached in can be varied quite a bit. Some things to note is that in both sequences, the assembly begins with the motor housing and has subassemblies for the stand, vent, switch, heating element, and handle. But in the second sequence, the motor and fan are made into one branch, while in the first, they are separate steps. Most notably, also, the first assembly added in the sequence is a heating element, while in the second sequence, it is the motor/fan subassembly, then housing cover. Sequence 1 also prioritizes adding the heating element, subassembly, then motor and fan, then vent, then switch, while allowing for ease of testing for each component in the motor housing at each step. Sequence 2 prioritizes adding the motor/fan subassembly, then handle, which does not create an ease of testing the components first. We conducted analysis on these two assembly sequences and identified the sequence 2 to be the better assembly sequence due to the criterions of ease of transferring and handling, ease of locating parts, ease of fastening/joining, and ease of assembling in parallel.
With the function component matrix, we can see the part with most function is the bend plate, and the part with less functions are the motor fix kit. With this matrix, we ensure that the boom covers all the essential parts for the heat gun.
Here is our bill of materials. We had two separate sources when acquiring the parts involved with this heat gun. The first set of parts came from a simplified CAD model, and the parts highlighted in blue came from an exploded view schematic of the heat gun. Since we are not concerning ourselves with any of the electronics, all of the electronics are purchased. We found many purchase costs from the company Master Appliance, the company that makes and sells the heat gun, as replacement parts. These costs have been highlighted in yellow, and we decided to take 80% of the cost, approximating that 20% of the price is direct profit for the company. This is still probably more expensive than it actually is, but it can give us a rough estimate, which we found to be about $170, which is highlighted in green. We then compared the components by their manufacturing costs and functional importance. We see that we want to direct most of our attention to the heating element sleeve and the heating element, as well as the motor housing and the motor cover. We're not going to be looking into the electronic assemblies as they're considered purchase material. We will also be looking into trying to eliminate the mesh, vent plate, the dial, and the switch plate, as they have low costs, but also low functionality.
Functional differentiation table here shows the functives that are the same for both the primary and secondary customer groups, such as delivering electricity and transforming the energy. It also shows the functives that are different between each customer group, such as shielding the heat and providing stability.
From the functional differentiation, we can find the assemblies and components that are platforms for providing the necessary functions to all customer groups, and the modules that support the primary function of the heat gun, but can vary to fit each customer's group's needs. We can see that the electronics in the heat gun are important to its function for every user, but parts like the stand subassembly or heating element sleeve can stand to change between users.
Here you can see the side-by-side differences in the primary and secondary customer variances. The primary customer utilizes a straight, large ported nozzle and a base plate that does not require an ability to attach to a surface other than through the force of gravity and frictional forces. The secondary customer's variant has a nozzle that can reach around corners and a base plate that can magnetically attach to ferrous metal beams or adjacent pipes. The common interfaces between the variant components would be the end of the housing element sleeve and the specialized nozzle and the stand arm and their stand base.
In our drafted assembly sequence, we can see that for the majority of the process, the product is assembled in the same way. This product differentiation can be delayed significantly in the sequence, allowing for more efficient assembly procedures.